Okay, welcome back to the Year 11 Maths Guide. Today I'm going to be starting to go through some of the dot points from the formulas and equations topic. The three we're going to go through in this video are as follows. So the first is to substitute numbers into linear and non-linear algebraic expressions, equations, and formulas. So by linear and non-linear, we mean, lines that are straight or not straight, all right? And they've got different expressions and equations that represent it, if they're straight or not. So linear lines, your x or your variables will always be to the power of 1. For non-linear expressions, your variables, such as x, will always be to a power that's not 1, such as x squared. So you might have y equals x, that's linear, or y equals x squared, that's non-linear. And you know that because of the power of the x there. The next dot point is to evaluate the subject of a formula given the value of other pronumerals in the formula. So if you get given other values of pronumerals in the formula or not, you should be able to rearrange a formula to make a particular letter the subject. So if a question says make y the subject of this particular equation, what it's asking for is that it wants y on the left side is equal to something. It just wants y on its own is equal to something. And that works for any variable. If you want to make x the subject, y the subject, any letter you want, that just means you want that letter to be equal to something. It doesn't care what it's equal to, as long as the only thing on the left side is that one letter that it's asked for. And the final dot point there is to calculate the distance, speed, and time with change of units of measurement as required, and stopping distances of vehicles using speed equals distance over time, and stopping distance equals reaction distance plus braking distance. So we've got to look at an example of how to do that as well, and converting between your units there. So if we start off with the first dot point, which is substituting numbers into linear and non-linear algebraic expressions, equations, and formulas. For this example, I've chosen a non-linear equation and we're substituting in a variable. There's nothing more complicated than just replacing the x everywhere you see it with the whatever value that they give you. So in this case, we want x to be equal to 4.5. So what I want to find is not y of x. I want to find y of 4.5. And all that means for my substitution is that everywhere I see an x, I replace it with 4.5. So y of 4.5 will be equal to 5 outside of 4.5 squared minus 3 outside of 4.5 plus 12. So it's just everywhere I see that x, I replace it with 4.5. And some examples you'll be able to do in your head, but for this one, we'll just use our calculator. So if you type that in, you're going to get 5 times 4.5 squared minus 3 times 4.5 plus 12. You're going to get 99.75. So that is the expression evaluated once we've subbed in y is equal to, x is equal to 4.5. Okay, the next dot point is to evaluate the subject of a formula given the values of other pronumerals in the formula. So for this question, we've got to make y the subject, and then after we do that, we then got to evaluate it by subbing in another letter for x or something, because that's what it means when it says evaluate. So if we evaluate it, once we've got y the subject, that's just an expression for it, but to evaluate it, that then means to sub in a variable or a number for x, so then we can actually get a number for y. That's what we mean when we say evaluate. So first step is to make y the subject. So you can see y is on both the left and right side of that equation there, and it's also on both sides there underneath square root signs. So the very first thing you should be doing is by undoing that, because you want to get, our final goal is we want y is equal to something. That's our goal, right? So we don't want y to be under a square root sign. We need to undo that. So the way we undo a square root sign is by squaring something. So what we're going to do is square both sides. If I go to square the left side, I'm going to get 3x root y all squared. And then on the right side, I'm going to get root 5y all squared. And now if I apply the distributive indices law, basically that square power applies to both the 3x and root y on the left-hand side. So I'm going to get 3 squared x squared root y squared. And then on the right, I'm going to get root 5 y, all of that is still going to be squared as well. So then on the left, 3 squared is 9, x squared stays the same, and then I've got root y all squared. The square root sign and the square simply cancel out, so you're left with y. And on the right side, similar thing will happen. The square root sign will cancel out with the square, so you'll simply be left with 5y. Okay, then since we've got y's on both sides of the equation, what we should do is bring all the y's to one side of the equation. So that's what I'm going to do now by subtracting 5y from both sides. Now I've got equal to 0 on the right side. Now what you'll notice is that I can actually take out y as a common factor, which is what I'll do. So I'm going to get y outside of 9x squared minus 5, and that is going to be equal to 0. So y is simply equal to 0 divided by that thing there. But 0 divided by anything is 0, so y is actually going to be equal to 0. So y will be equal to 0 regardless of what x is. So you can try this out yourself. If you sub in any value for x and rearrange it, you're going to get y is equal to 0, because y is equal to 0 over 9x squared minus 5. Regardless of what x is, you're going to get 0 every time. But if y was not equal to 0, say y was just equal to 9x squared minus 5, not 0 over that, then you'd simply sub in an x value for this expression, and then you'll get another value for y. Okay, so that's that example. Let's move to the final dot point. Calculate distance, speed, and time with change of units of measurements as required, and stopping distance of vehicles using that, and stopping distance equals reaction time plus braking distance. So this question basically tests all the elements in that dot point there. So if we've got a car traveling at 100 kilometers an hour, and the driver's reaction time is 1.2 seconds, and the braking distance is 35 meters, calculate the total stopping distance. So we know we need to add our braking distance and our reaction distance. So our total stopping distance is going to be equal to 35 plus our reaction distance. Now we know our reaction time is 1.2 seconds, but we want the reaction distance. So this might be an example of someone on the motorway. They notice a crash in front of them, and it takes them 1.2 seconds to respond. So in that time where they're reacting to it and they haven't worked it out yet that an accident has happened ahead, they're obviously still moving. The car doesn't stop while they're still reacting. So that's what the reaction distance is all about there. And what you'll notice is that the other units we're given are meters and seconds, but then the speed is kilometers per hour. So the very first thing we should do is convert 100 kilometers per hour into, it's going to be equal to something in meters per second. So how do we do this? Well, I just break it down, and I keep breaking it down until I get each unit to exactly what I want them to be. So first of all, with kilometers, we don't want kilometers, we want meters. So 100 kilometers is equal to 100,000 meters. So I can replace 100 kilometers with 100,000 meters. So the car is going at 100,000 meters per hour. And now if I convert the hours to seconds, what I'm going to have to do is, 1 hour is 60 minutes. There are 60 seconds in 60 minutes. So I'm going to get 60 squared, which is equal to 3,600. So the car is traveling 100,000 meters every 3,600 seconds. But I don't want how far the car is traveling over 3,600 seconds. I want how far the car is traveling over 1 second, right? I want meters per second, not per 3,600 seconds. So I'm going to have to take 100,000 and divide that by 3,600. So that's exactly what I'm going to do. And I'm going to get a speed of 27.78 meters per second. So the car travels that many meters every second. So in 1.2 seconds, how far will the car travel? Well, we want distance. So if we use our distance, I wrote this wrong. So if we use our distance, speed, and time triangle, what we want to find is distance. So we cover that one up, and what we'll be left with is S and T at the bottom. So distance is equal to speed times time. So the distance is what we're after. Our speed is 27.78. And our time, well, his reaction time is 1.2 seconds. So now we've got to get our reaction distance. So if we type this into our calculator, we're going to get 33.33 meters. So that's how many meters the car will move while he's still reacting. And then when he does react and he does brake, it's then got to take another 35 meters for the car to stop. So the total stopping distance is simply going to be, 33.33 plus 35, which is equal to 68.33 meters, approximately. So that will be the total distance required for this car to stop if it's traveling at 100 k's an hour and his reaction time is 1.2 seconds and his braking distance is 35 meters. So that is it. Thank you. I will see you in the next video.